Okay, so in your notes to me, you said that you know the region is unbounded. That's great, and you understand that there can still be an answer. And the reason why here is, note, it's asking for us to find a minimum. As our values, let's say we have a corner point right there, and as our values go through here, the x and y values are getting larger and larger. And if you look at the thing we're trying to minimize, as our x's and y's get larger, so will our thing we're trying to, the objective function. So therefore, if we're trying to find the minimum, it does us no good to get bigger and bigger x's and y's. That's why this thing still has a minimum, even though it's unbounded. Now, if it was, something like this, where it was unbounded, where we didn't have the x is greater than 0, y is greater than 0 constraint, and maybe we had a graph that looked like that and we were shading this way, and it was unbounded, well, then there would be no minimum because it's shading down, and as our values get more and more negative, that would be a good thing. So therefore, this is the scenario where unbounded min is bad. Where in this graph, if instead of asking for a minimum, if it asked for maximum and it was unbounded, then you'd say there is no maximum because it's unbounded. So anyway, so I hope that clears up or just solidifies what you were already thinking. Now, on to where your problem is. Your graphing, I'm assuming it's good. Because it's just a rough sketch. That's all you really need. You don't need these things to be perfect, because all you need to see is your corner points. So I'm just going to highlight those in red real fast. So we have one corner point right here where the two lines meet, where the two lines intersect. You're going to have another corner point where whichever graph this is intersects with the axes, because we have the restriction that x and y have to be greater than 0. So once it goes negative, we're going to be bounded along that axis. And then similarly, up here on the y-axis, we're going to have that limitation as well. So our corner points, we're going to be bounded within here, if that makes sense. So we need to check 3 points. We need to check the point where these meet. We need to check the point wherever that value is. We need to check that point wherever that value is. And then we're going to take each of those 3 points and substitute them into this function. So making the assumption that 1, 1 is where these two graphs meet, and one of them has this one has a y-intercept at 10 and an x-intercept at 10. We just have to test the 3 points. And keep in mind that the goal is to have the minimum c, whichever of these 3 points, when we substitute in the x and y value, whichever one gives us the smallest c value, that's our winner. So here we go. So our c is equal to, it was just x plus y, correct? Yep. C equals x plus y. So when we go ahead and substitute in the point 1, 1, well, that's going to be c equals 1 plus 1, which means c equals 2. Okay, then let me take this out of red. Then when we do the point 0, 10, well, that's just meaning 0 plus 10, so it gives us a c of 10. So looking between these two, 2 is less than 10, and we're looking for minimum, so this one's out. Now let's check the last point, the point 10, 0. And I know this is probably head math for you. If it's not head math, 10 plus 0, we probably need to go back to another math class. Anyway, okay, so c equaling 2, c equaling 10, so we know 2 is less than 10. So therefore, the minimum, the point that gives us the minimum value is the 1, 1. So therefore, when we have a x value of 1, a y value of 1, we have a c value of 2. I hope that makes sense. I hope you enjoyed my wonderful math humor, and we'll see you at the next video.